once we understand how to add or insert an elements into a list, BST list here, we know there's going to be a problem. It is depending on the input that you insert. Like if the input happen to be like sometime in the middle, come first, then this is going to be a balanced tree. Wedging to the left and right is going to be even. But if we said, okay, if the first item that you insert happen to be small values, then the wedging going to be go more to right, because the greater values is going to be on the right. Since the first element is small, which becomes the root. Same. Last one, if you look at if the order list insert into BST, order list means the left is the smallest. Then the left become the root right away. Because first time we insert, we always set the first element to get the root. In this case, when you start to insert, the order list is going to be like a linear list. Like a linked list. It's no longer a tree anymore. So that's the problem with the tree shape here. It depending on the inputs. So if input is in order, then BST pretty much just linear list. We're going to look at how we're going to balance tree. Now, we're going to look at this remove operation first before we look at how to balance the tree. Because depending on when you insert. So the most complicated operation of the BST is the remove. Because we want to ensure we remove an element, we maintain the BST property after we remove. So the setup for the remove operation is the same as for add operation. We have the recursive remove methods invoked through the remove method. So we're going to use recursion with the arguments equals to elements to be removed and the subtree to remove its form, passing in. So the recursive method returns a reference to the revised tree. The remove method returns the Boolean value stored in found, indicating the result of the remove operation. So this is called remove, and we have root equals to recursive remove and pass in elements to remove and the root itself. Now we have to return if we found things to remove or not. So let's look at recursive remove, how we implementing it. First, check if the root is null. If null, then file is false. We don't have anything to remove. Else, we start to compare if the elements to remove is on the left. Then we're going to recursive remove the left, and we have to set the left. Okay, why set the left? We have to set the left, and we have to set the right if it's on the right to remove. Let's look at the image here, right? When you remove, so for example, if I remove Z, we have to set the right, Z is the right. That's why we have to set to null. Right has to set to null. That is the first case that when we remove a leaf node. If the leaf node is to the left, like L, like that, we set Q to null. So that's why we have to set, right? So that first scenarios. Second, if you remove the node that has the child, like R, then you have to set the link of Q, set right to point to Z, which you have to get whatever R dot right is. So that is a 0 if you remove your node with one child. But what happens if you remove the node with two children? So this one is not easy because you have to make sure that you still maintain the BST property. Oh, in order to maintain that, we said this is the node that has on the left children group, and we know the most on the left children group. This should be a candidate to replace that, because this is either greater than or equals to the left. So that's why we're going to take the most on the right to replace Q to keep the property, right? The most on the right of the left to replace that node root. And then that P is going to be always greater than the one on the left or equal. And also less than the one on the right in this case. Now let's look at the algorithms. So we understand the principle of remove, right? There are three cases. When you remove the leaf, when you remove the node with one child, when you remove the node with two children. So remove nodes, we going to pass the tree in, and it's going to return the reference to the BST node. If tree.getLeft is null and tree.getRight is null, return null. This is the leaf node. Right, return null. That's why when you set, remember recursive main function, we can set it to null. The parents to null, right? Now, else if getLeft is null, that means children's in the right node, right? One child, right? Then we return getRight. Remember when we return getRight, it's going to set that to the right. We just talk about recursive remove here, algorithms. Right. Same. If getRight is null, then we return left. Else, that means two children. Case of two children now, right? So this is case of leaf, this is case of one child on the right and one child on the left. This is case of two children. So in this case, we're going to have to find predecessors. Predecessor is pretty much just P, the one that is the highest of the left, right? So we set info of predecessor of getInfo, and then we do set left. Recursive remove predecessors of getInfo. 3.getLeft. Okay, let's look at this logic. So let's look at get predecessors logic. So the logic for predecessor is the maximum value in tree's left subtree. The max value in a binary search tree in its rightmost node. Therefore, given three left subtree, we just keep moving right until the right child is null. Right, so that's the algorithm's logic. Right? When this occurs, we return the info reference of the node. So we pass the tree in while getRight not equals to null. then we just say tree equals to tree.getRight, and it's keep doing that until it's equals to null. Then we get the info. So that's how we implement the get predecessor, right? To get the max value of subtrees of the left node, right? Of the left subtree. Because we passed, if you look back, we passed tree.getLeft in. Then we get the most maximum values, right, of the left subtree back as the data. Now when we get the data, we can set the tree.setInfo to the data. After we set, it's just like this picture, right? We take P and we set, right, to the data, we just J to data. But the data P itself, we have to set the node to point to the left and point to the right. Then we have to link back, right? So that's why we going to set the left, right? Set the left, because it set the left. Okay. And we know this is going to remove predecessor node, recursive remove, pass data, tree.getLeft. This is going to return the node that you're going to remove. The method used to remove a node. Let's look at this. So we're going to look at this method now, recursive remove, before we set that. So we have the elements remove. So it's going to look at the elements at the node and recursively doing that, remove. Until we find the node remove. Then we find our predecessors, return that. And then we technically go back and find again if there's nothing to remove. So just keep looping until the end. So technically what we do here is we found a place to remove, but we don't remove that node, we replace just the data into that node. Because the link's still the same. We don't have to worry about link. But what we want to worry is about set this link to null. Right? Either it's left or right, we don't know. But we have to set it to null, right? So that's why first we find the predecessors. From that logic, we get the maxed data from the left subtree. We set the info to replace that. We don't have to worry about the links, it's already linked, we just replace it in full. But we have to recursively move the data out. That's why we pass that data, which is the P. To remove P, that's why we have to, depending on recursive again. And it's going to get into the leaf and remove the leaf by doing this. This statement is pretty much just this statement. This one. But instead of removing the elements, we want to remove that P out. After we move P, right, and replace the P to the Q. That makes sense? So that's why this statement pretty much just remove the predecessor node. That's what it's